Hello, everybody. This lesson is the first in the next chapter. We just finished the quadratics unit, so we're looking at all the different types of all the different details to quadratic relations. And now we're going into exponential relations, which is just another type of a nonlinear relationship. Okay, so we're going to look at exponential growth first. And so the example we're going to look at is, one sec, I just need to pause quick. I just realized I gotta find the smart board. All right, we're back in business here. Okay, so this graph shows the volume of a batch of dough or pizza dough that's growing exponentially over time. And so what does that mean, I suppose, right? We're kind of going through here. And so just looking at the graph, what was the initial volume? So you can easily identify the initial volume being there as 0.5. So it's 0.5 liters based on that, right? So the initial value. Just reading from the graph for now. The initial value here at time 0 and then 1, 2, 3, 4, 5 in minutes, right? So at 0 minutes, since mixing up the dough, starts out at 0.5 liters. And then it says, what is the volume of the dough when the initial volume doubles? A weird way of asking the question, but basically, I might ask this one really more so, right? How much time does it take for it to double? But they're just getting you to recognize where the doubling spot is, which is at 1 liter. That'd be the volume is doubled. And you can see that that's after 3 minutes, right? So you can see over here to 3 minutes for that double volume. So obviously the double volume is pretty obvious here. It's the 0.5 times 2 gives the 1 liter. I suppose maybe you could do that mathematically or on the graph, right? They should agree with one another. And then how much time did it take? Well, it took 3 minutes. So 3 minutes it took for that to double. And then it goes on to say, okay, well, how much time does it take for the dough to double in volume from 2 to 4, or let's go even just like the next double and then the next double, right? So let's go from the 1 liter to the 2 liter, and then from the 2 to the 4, and so on, however many we can see on here, right? So 1 liter up to 2 liters is another double. And you can see, we can look at how long that took. So let's go across to there. So we went from 3 up to 6. So that's another 3, right? So 3 minutes again, the double. This one was 3 minutes, obviously, 0 to 3. And then 3 up to 6 is another 3 minutes. So this one is 3 minutes. And then let's go from 2 to 4. So 2 all the way up to 4. Again, you can tell you're just doubling your volume. Not wrong to say that. Notice that the volume is increasing by in 3 minutes is not really constant, but it is doubling. That's kind of a consistent thing, let's just say, right? So yeah, so that's 3 minutes as well. How do you know? Well, it's from the graph, right? But just reading from the graph. And then it says compare this to the time you've measured earlier. Obviously, they're all the same. So basically just getting you to recognize that the situation we're talking about here is that it's always doubling in 3 minutes. So that is an exponential relationship. Okay, so this situation is exponential. So this is exponential growth specifically. So this is exponential growth. Right? So we're going to look at the details of that and analyze it a little bit more. So what was the doubling time for the pizza dough? Obviously, the doubling time was 3 minutes. explain, I guess you could say that the volume is doubling every 3 minutes. Does the time for the volume to double depend on the points used? No. Basically, the doubling time is going to be 3 minutes between any 2 points, one where you're doubling, right? So picture point 1 or volume 1 to volume 2. So volume 1 to volume 2, where we're talking about if it's times 2, then that took 3 minutes. Anywhere along the way. Is the volume of the dough increasing at a constant rate? Well, no, it's doubling all the time in 3 minutes, but it's not increasing at a constant rate, because if you look, the volume is increasing faster and faster, right? So the volume is increasing faster and faster. So it's a big old no for that one. It is doubling every 3 minutes, which is kind of like something's constant. But if you look here, you have this much extra dough, and then you have this much extra dough, and then you have this much extra dough, and it's just going to keep growing exponentially. That's exactly what that is, right? So the doubling, yeah. So yeah, there's a constant rate of doubling, but certainly not a constant increase in the volume. Okay, so let's start to analyze the numbers for this. Shocking, I know, right? In a math class. So here we go. So we're going to make a table of values for the volumes, and they're pretty obvious, right? You just double each time, right? So if I multiply by 2, I'm going to get the 1. If I multiply by 2 again, I'm going to get 2, and multiply by 2 again, I get the 4, and so on, just like we did, or just like we looked at in the graph. If I had have given you the information as the volume of the dough is doubling every 3 minutes, this table would make sense. The every 3 minutes is here, right? So we've got the every 3 minutes check going on here. So that's why the table doesn't go 0, 1, 2, 3, 4 like normal. So this is every 3 minutes. So the points of interest are the 0 and the 3 and the 6 and the 9, right? And the corresponding volumes are just based on that logic. Okay, so the next thing we want to do is we want to start to figure out what the equation would look like for this. The equation, if we know the equation, that's basically the math of the relationship itself, right? Okay, so just like in grade 9, knowing y equals mx plus b is the math for a line, and grade 10 and what we reviewed recently, the ax squared plus bx plus c, the math of a quadratic. We're wondering about what y equals for an exponential growth situation. Okay, and we'll be able to figure this out. So what we're going to do is we're going to think about what the calculation would be to get each volume. Okay, so obviously this 1 here comes from 0.5 times 2, right? 2 came from the 0.5 times 2 times another 2, right? So I'm going to say times another 2. And then the 4 came from the 0.5 times 2 times 2 times another 2. Trying to separate that extra 2 each time just to sort of visualize it. So we're getting this idea here. And so in the end, you can kind of, well, let's just sort of summarize this a little bit. 0.5, and then we have 2 to the power of 2, because there's a simpler way of saying times 2 times 2 in math. You could say times 2 to the power of 2, okay? So let's put that in place there. And then for the fourth, for the volume of 4 at the 9-minute mark, so that's 1, 2, 3 doublings, we'd have 0.5, and it's to the power of 3, right? The 2 to the power of 3. I think these equations should kind of just you can formulate them pretty easily looking at where the numbers came from. I do this all the time. I do this one in grade 9 with linear. I do it in grade 10 with quadratics for trying to figure out a special equation format. Just think about where the numbers came from and put it in that terminology, right? So if we're trying to make an equation here for this, what would that be? Well, obviously we have that starting value. Okay, so let's point that out. We got that starting value right there. starting or initial value, whatever you want to call it. So we're going to have that starting value of 0.5. So it's going to be equal to 0.5. This is a little tricky where you think, okay, well, what's the rest of this? Well, the doubling, right? So as it doubles, we've got that times 2 all the time, right? And even in the power version, we've got the times 2. So we've got the doubling, right, in there. So we got the 2. And then the weirdest part is the exponent. Okay, so we need to look at what the exponent would be based on the t. Okay, so we need to have an exponent based on t somehow. Okay, so you have the 3, and that leads to an exponent of a 1, and the 6 leads to an exponent of a 2. And by the way, I put in there, there's a 2 to the power of 1 is supposed to be just sort of understood to be the power that's equivalent, right? And a 9 goes to a power of 3. This one technically is a 2 to the power of 0, but we don't need to talk about that one. But 2 to the power of 0 is 1 if you check with the calculator. We can discuss why later on, but maybe not the best time right now. Don't want to lose anybody. So 3, what do you do to get a 1? 6, what do you do to get a 2? 9, what do you do to get a 3? Well, you might notice that you're dividing by 3, right? If I divide by 3 each time, then that gives that number, right? 9 divided by 3 is 3. 6 divided by 3 is 2. 3 divided by 3 is 1. Okay, so really this exponent up here is a t divided by 3. I almost want to put it in black here just to illustrate how we noticed it, right? So dividing by 3, I will try again with that. There we go, right? So that is what the formula should be. We basically have the volume. This equals here. I should have over a little bit farther. But basically, we're saying, what's the volume equal to, right? So we have volume equals this. Volume equals 0.5 times the 2 to the power of t over 3. Okay, so that's not some mysterious equation that doesn't make sense. It's an equation that's based on the results we saw. We're starting with that initial value. We have the multiplication factor of a 2 that we're told, or we just saw in the data. Sometimes you're told it, sometimes you're just, in this case, we saw it from a table of value or a graph. And then we have that t over 3, which isn't mysterious. We just see that that's what the numbers end up being. So the logic of it is, I hope you just see, is kind of undeniable here, right? So we have that doubling thing going on, and we have the what could have been tripling, by the way, right? So it could have been tripling, in which case we would have had a 3 in there just as an extra note. And then up here, I forgot to put an arrow for it, but this is the t over 3, right? This is the time period t, and then we're divided by that doubling period, right? So this is t divided by the doubling time. That's what that one ended up being. So you just kind of have to say, okay, well, that's what it is. Okay, so we now have an equation for exponential growth, where you're going to have your initial value. So I don't know, I'll call it like I. Let's say for initial value, have your multiplying factor. So I'm just making up letters as I go here, and then we'd have like the t divided by your doubling period. So whatever, I'm just going to put a number sign in there. That's just roughly showing it for now. Okay, that's the idea. So we're saying that equation should look like this. I'll show you some proof of that or whatever. This is a graph from a program, any program. You could have done it with GeoGebra and that too. This one's just an old school geometry sketchpad. So show that point, the coordinates of that point are right there as 0 and 0.5. So there's your initial volume of 5 and your time at the starting time of 0. And then if you drag this point along, it goes to all the new values. So it's not going to nail the number unless I try really hard to get it. It's even actually having trouble calculating perfect values. Oh, that's also here because this thing is in this 0.33, which I should have probably done this. Original take on this thing. So if I did divide by 3, probably going to give me better numbers here. So if I chance that I'd be able to drag this to exactly 3 and get it exactly 1. But again, the computer's having trouble with pixel calculations, but it did manage to at least nail that one. The point technically goes at a certain pixel, right? So then it tries to estimate the number as best it can. So there's the 3 and the 1, and then go up to the volume of the 2, and there's the 6 and the 2, and so on, and then go up to the 4, all the way along. You get your numbers all the way along. So there's the 9, and so on. Okay, so you could keep going even, right? So we get to 8. We had the volume of 8 down here at 12, and so on. Okay, that's exactly the same graph, just extended, and you can look at any spot you want digitally and so on, just like reading from the graph. Okay, so that's an exponential relationship there. Another common way to introduce the exponential or give the exponential information, we should cover that too. So sometimes you're given, instead of like a doubling factor or a tripling factor or a quadrupling factor or whatever, sometimes you're given a growth factor, and it's often written as a percent. So this little example of a wolf reintroduction project where they introduced 25 Canadian gray wolves in Montana, and they when they studied the population, they found it was increasing at a annual growth rate of 20%. Well, an annual growth rate of 20%, this is just a summary of exactly what was in the paragraph there. An annual growth rate of 20% is exponential growth. Okay, so just recognize that, well, we'll see, but this is exponential growth. Okay. So we'll see how that works and what the numbers look like for that one. Okay, same idea. Got this 25 population. We want to increase by 20%. Okay, so basically this next number here has to be equal to the 25 plus 20% of 25. So I write it like that for now, I suppose. I'll probably write less in the future lines here, but so that would be 25 plus 0.20 times 25, which we have 2 ways of going about this. I'm going to show both. Obviously, you could just calculate it. So 0.2 times 25 gives us 5. So we could say, okay, we got 25 plus 5, so we get 30. Okay. Problem with doing it only that way is that we wouldn't be able to see the pattern as well. And so I'm going to also show the other version of things. So I'm going to say equals this or this, in other words, right? So we've done common factoring recently. There's a method to the madness of how the course is designed here. If we common factored out the 25, then we'd have a 25 out front, and we'd have times 1 from the 25 divided by 25, and a 0.20 from the 0.20 25 divided by 25. Okay, and so really this 30 is actually equal to, I guess I should show more here. This 30 is really equal to 25 times 1.2. And you might have seen that with just how to calculate tax in previous classes, right? You can multiply by 0.13 and then add that onto the total, or you could add the 0.13 to the 1 and just multiply by 1.13, and it gives you the total answer right off the bat. Here I'm writing 1.13 because of my example I'm talking about. So 1.20, and this was the 5, and so on. So this right here is the equation, the part that helps you figure out what the equation is. Okay, so we would have just had a 30 here as numbers, but the thinking about what made those numbers is a bit more complex for this one. Okay, so this time we would. How am I going to fit this in here? I'm just going to shrink this guy down a little and move it up. Okay, so that's the thought process for that one. Let's streamline this a bit. for this one and say, okay, well, for the second one, we have that 30 we started with, right? Or we could think of the 30 we started with as this thing. That's 30, right? So let's start with that. So we're going to start with the 25 times 1.20. That's our 30, basically, right? And so that has to get multiplied by another 1.20. Essentially, we now know the process to get from one step to the next is to multiply by 1.30. 1.20, sorry. Right? So if you do that again, times 1.20, squeeze it in there barely, then we get 36. Well, check that out. So do 25 times 1.20 gave the 30 times another 1.20 gives 36, right? So this one we could summarize as 25 times 1.20. This is where the exponential record of things comes in, power of 2. And then we're going to take that result from the previous line. So let's have the 25 times 1.20 times 1.20 times another 1.20. Obviously now that's going to make it 1.20 to the power of 3. So this one down here, then we can say, oh, okay, so the population of the wolves. So, oops, I copied and pasted my table. I kept the word volume there. This should be population. I was just looking at what letter to use. Population P. And this could be number of years N. Maybe something like that. I might have to change my other equation as well. But this N value here is going to be equal to that initial population of 25 times 1.20 to the power of what? Well, in this case, you can see that the number was really just the exponent, like the number of years is the exponent. That was the power of 1. This one's the power of 2. This one's the power of 3. Just different situation, right? Where it's really because it's a 1, 2, 3 situation, 1 year, 2 years, 3 years. If we actually said it was 20% increase every 3 years, it would have been t divided by 3 again. Okay, so this one is going to be the n, just n straight out. But I'll make a note of that. Let's do that right now. If it was, increase by 20% every 3 years, then that would be the exact same as what we just saw in the other one, right? That would be n, or population. Sorry, this should have been a p up here. So p for population, the p would equal the 25 times the 1.20, and that then would be n divided by 3. So what happens there is if you put in, for n equals 3 years, that's 1 increase by 20%. Well, that would go in as a 3 over 3, which equals a 1 20% increase. Okay, so watch for that as well. It's the same as before. This number ended up being like 43.2. Basically, just take that number and multiply it by another 1.2 and 1.20, same thing, of course, 43.2. That's where the math kind of becomes an estimate for the population. 0.2 of a wolf, probably. But it's obviously approximately you're going to expect to see 43 or 44. More likely 43. So what equation would represent this? Exactly this, only of course I did forget to put the new variables in there when I was just making this lesson for us. But this would just be like an n or something. And it just makes sense to use variables that make sense in the context of the question. So that's why I'm using p and n instead of v and t. Population in number of years instead of volume after a certain amount of time in minutes. Okay, so the 25 is your initial value, the 25 wolves. Here's your population increasing by 20% each year. This is a little blurry here, but when the growth rate is given as a percent increase, we end up with this like 1 plus r. okay? And that R is the percent expressed as a decimal. So for example, here we had 20%. Well, percent literally means to divide by 100. Percent means, per means divide, cent means 100, right? So 0.20. So that's going to give us our number example of 1 plus 0.20, giving us our 1.2 or our 1.20. Okay, so that's exponential growth, just a new equation form to know, recognize, understand, and so on. And eventually we'll get to the point where we graph those as well and get more and more familiar with all of it. Okay. The next slide I have says, graph this thing and see what it looks like, basically, right? And we can find out some things from this. So what's the doubling time for this situation? If we graphed it, we'd graph the 25, so the 0, 25, and the 130, and so on. So 0, 25, 130, all the way along 2, and whatever that number was, and 3, and so on, right? That was the 36, right? So this one was the 36. And so on and so on. If you look at the graph and say, okay, we started with a population of 25, when do we get to double it and end up, just to sort of connect the two examples together ideas wise, right? You could do that in this case. You could say, okay, well, how long does it take to double? And so you're like, okay, we went from 20 to 50 in, approximately what? Looks like about 3.75 or 3.8 or something years is an estimate from a graph. There is a mathematical way of doing that, but we're not doing that in this lesson, right? Yeah. So that's it for that. So each one of these, I want you to complete like just talking about what the growth factor would be, right? So if we did one of these together, this is where you have to add on it as a decimal. So this is 5 divided by 100 equals 0.05. Add that on, you get 1.05. That's the idea there. We're doing, and then working backwards from that, we'd have to have said, okay, we have the 0.5 multiply 0.05 times 100 would be 5. And so we'd work backwards to it's a 5% increase. Okay. Determine the doubling time for each graph is an example just like what we did. Just on the previous page there, but yeah, we're starting with a volume of 1, so a value of 1 and doubling. So you can tell it doubles in 1 unit, whatever the units are, and so on. This is all the kind of stuff we just did. Okay, so hopefully that makes sense. Certainly post questions if you need any help, and I hope that works for you. Bye for now.